In this videotape, we will be discussing circles. As most of you know, a circle is a set of all points, a fixed distance, which we call radius, from a fixed point, which we call the center. Here's the radius, here is the center. It's a set of all points in the plane, a fixed distance, which we call the radius, from a fixed point, which we call the center. The perimeter of a circle, the distance around the circle, is known as the circumference. The circumference of a circle is just a fancy name for the perimeter of a circle. The line segment that goes from one point on the circumference to another point on the circumference and passes through the center of a circle is known as diameter of the circle. The diameter of the circle. If you were to extend this radius until it hit the other side, you would have a diameter. The diameter is a special example of a chord of a circle. A chord of a circle is a line segment connecting 2 points on the circumference. If the chord goes through the center of the circle, it is called a diameter. An extended chord, or a line segment which cuts the circle in 2 points, is known as a secant. You can think of it as either an extended chord or a line segment which cuts the circle in 2 points. A line, rather, that cuts the circle in 2 points. A line which cuts the circle in exactly 1 point is called a tangent. A tangent line, or a tangent, is a line which touches the circle at exactly 1 point. An interesting thing about tangents is that the tangent happens to be perpendicular to the radius, which is drawn to the point of contact. A tangent touches the circle at one and only 1 point, which we call the point of contact. That is the point of contact, or the point of tangency. The radius, drawn to this point of contact is perpendicular to the tangent. Now, a long time ago, it was observed that for all circles, big ones, little ones, middle ones, if you were to figure out the circumference of the circle, and compute the diameter of the circle as well. The diameter is here, the circumference, the distance around the circle. For a circle of any size, big one, small one, whatever, the circumference of the circle, C, divided by the diameter, always came out to be the same quantity. If you have a little circle, obviously you have a smaller diameter, but you have a smaller circumference as well. It turns out that the ratio, C over D, this quotient, the circumference of the circle divided by the diameter, is always the same number. You can imagine you have like a hoop. You measure the distance around the hoop, that's the circumference. You go across like this and measure the diameter. That quotient is the same regardless of the size of the hoop. And since this number always came up a lot, it was given a special symbol. The symbol for this was pi. The Greek letter pi represented this special ratio, the circumference of a circle divided by the diameter. It came out to be approximately 3.14. It's really an irrational number, which means its decimal representation never terminates and never repeats. But to 2 places, it's 3.14. Some people use the fraction 22/7. It's also an approximation. Don't feel that 22/7 is exactly pi. It's just an approximation with fractions, which comes out about this. But pi itself is an irrational number. It never repeats the decimal representation. It never terminates. Okay, but for all circles, you could try this yourself. Okay, if you have like a hula hoop, something like that, you can figure out the circumference divided by the diameter, and your answer should come out a little over 3. Okay, it's a pure number. There are no units here. If, in other words, if C is in feet and D is in feet, the feet cancel out, and you wind up with just a pure number. Okay, pi represents the circumference divided by the diameter for a circle. If you were to take this relationship and multiply both sides by D, okay, you have C is equal to, C over D is equal to pi. Multiply both sides by D. D represents the diameter. Okay, here the circumference is C, D is the diameter. The circumference is C, D is the diameter. Multiply both sides by D, and you get, here the D's cancel, C is equal to pi D. Or C is equal to pi times 2r. Remember, the diameter goes from one end of the circle to the other end of the circle, passing through the center. Since a radius goes from the center to a point on the circumference, it stands to reason that D is equal to 2r. The diameter, for any circle, the diameter is equal to 2 times the radius. 2 radii extended to form a straight line segment give you the diameter. D is equal to 2r. Okay, so you can either write that C is equal to pi D or C is equal to pi times 2r. The second formula is usually written 2 pi r. Okay, it means the same thing, pi times 2r or 2 pi r. Okay, here we have 2 equivalent formulas for the circumference of a circle, and of course these are perimeter formulas. The circumference of a circle being just a fancy name for the perimeter of a circle, or the circumference. Pi d if you happen to have the diameter, or 2 pi r if you have the radius. Let's look at a typical example. Let's say we have a circle and the radius is 3 inches. And you're asked to find the perimeter or the circumference of the circle. The circumference is 2 pi r. Okay, it's 2 pi r here is 3 inches. So we get C is equal to 6 pi inches. Now don't be upset by this 6 pi business. Remember, pi is a number over 3. It's 3.14 about. So 6 times 3.14 comes out a little bit, comes out over 18, 18.8 or something like that. So this is a number. It's a certain number of inches. The pi is just a shorthand way of writing this irrational number 3.14 something. Okay, but don't be confused by this. This is a specific number of inches. If pi is a little over 3, this comes out over 18 inches. Okay, but it's a measure of the distance around the circle. Okay, now to find the area of a circle. Okay, originally, well, let's put it this way. Up to this point, we've only considered area of figures that are composed completely of straight sides. We had triangles and a whole bunch of quadrilaterals, and we learned how to find the area of these figures. Okay, the circle is the first figure that we've come across that has a curved boundary. So we have to sort of adjust our interpretation of what we mean by area. Okay, you might inscribe a square in the circle. Okay, that would be a square inside the circle, where each of the 4 vertices of the square lie on the circumference of the circle. And you could say, well, look, I know how to find the area of this square, and that's a rough approximation to the area of the circle. On the other hand, you might say, well, instead of a square, wouldn't it be nicer if I put a 5-sided figure in? Well, just imagine these came together at a point on the circumference. Inscribe a 5-sided, a pentagon, in the circle. Remember, any figure composed completely of straight sides, no matter how many, we only worked through quadrilaterals in the earlier tape, but any figure composed completely of straight sides, if you start here, say, and draw line segments to all the other vertices, what you do is you break this figure, no matter how many sides it started with, into a bunch of triangles. And since you can find the area of any triangle, obviously you can find the area of any figure composed completely of straight sides. Okay, so I can find the area of this 5-sided figure, and that's a better approximation than the square was to the area of the circle. On the other hand, look at it this way. Let's say I took a 10-sided figure and inscribed it in the circle. In other words, let me cut each of these sides in half. I think you will all agree that the area of this inscribed 10-sided figure is an even better approximation to what we'd like to call the area of the circle. Better in the sense that the region that is outside of this 10-sided figure but inside the circle is becoming smaller and smaller. Okay, what we could do is define the area of a circle to be the limit of the area of, say, an n-sided polygon, a polygon of n sides, as the number of sides grows very, very large. Okay, working that through, you would be able to come out with the following formula for the area of a circle. Okay, if you work through all of the algebra, you could, and you need some calculus as well, which is an advanced mathematics that you don't have yet, but you would be able to show that the area of a circle, okay, using that definition, that the area of a circle is pi r squared, where r represents the radius of this circle. Okay, let's go back to the example that we had over here. The radius is 3 inches. We want the area. The area is pi r squared. That is pi times 3 inches squared. That's pi times 3, or 9 pi square inches. Three times 3, that's 9 times pi square inches. And once again, remember, pi is over 3. This comes out over 27. I think it comes out to be 28 something. Okay, but it's a specific number. Okay, 9 pi square inches for the area of that circle. Now, sometimes we have reason to want to find the area, not of an entire circle, but rather of just a portion of the circle. Okay, if you consider, okay, the entire circle, a portion of the circle would be something like this. You can think of this, say, as a whole piece, a whole pie, and we're interested in the area of this particular slice. Okay, this portion of a circle is called a sector of a circle. It's the portion of the circle intercepted, okay, by 2 radii. Okay, and this portion of the circumference, okay? It's bounded by 2 radii and some of the circumference of the circle. This is a sector of the circle. A sector of the circle, it's a piece of pi, okay? And we want to find the area of the sector of the circle. Okay, let's say we know the measure of this angle. This angle, okay, is called a central angle, an angle formed by 2 radii. Okay, they come together at the center like that. This is a central angle. Let's say in this particular example that this angle is 60 degrees. Okay. Now, the trick to finding the area of a sector of a circle is to figure out what portion of the entire circle this sector is. And this is done by using the angle. You know that the central angle for the entire circle would be 360 degrees. In other words, one complete rotation, okay, is 360 degrees. So we ask ourselves, what portion is 60 of 360? 60 degrees over 360 degrees is 1/6 of the circle. Okay, this sector is 1/6 of the circle. The sector is 1/6 of the entire circle. (360 degrees for the entire circle and 60 degrees of the entire 360 degrees. Okay, now all we have to do to get the area of the sector of the circle, or the perimeter of a sector of a circle, would be to figure out the area of the whole circle, the perimeter of the whole circle, and to take 1/6 of that. Okay, for the area, we want the area of this sector, okay, with the 60-degree angle. That's going to be 1/6 the area of the entire circle. Let's say the radius in this case is 12. Well, all the radii of a circle are equal. Okay, so if this is 12, that's 12 as well. The area of the sector is 1/6, in this case, the area of the entire circle, 1/6 pi r squared. That's 1/6 pi times 12 squared. 1/6 times pi times 12 times 12. 1/6 times 144 pi. And 6 into 144 goes 24 times, so you get 24 pi square units for the area of the sector. The entire circle would have area 144 pi square units, but the sector, which is 1/6 of the entire circle, has area 24 pi square units. If the angle, by the way, had been 30 degrees, then you would say 30 over 360 gives us 1/12 of the total circle. And here we use 1/12 of pi r squared. And we would have wound up with 12 pi square units for the area of the sector. Okay, now we want the perimeter of this sector. Okay, that's going to be 12 plus 12 plus this portion of the circumference. And this portion of the circumference is 1/6 the total circumference of the circle. Remember, the perimeter of the sector would be the entire distance around the sector. So you'd have 12 plus 12 plus whatever this is. That's 1/6 the total circumference. Okay, the perimeter here of the sector, once again, with a 60-degree angle, is going to be the radius plus the radius plus 1/6 the circumference of the circle, 1/6 times 2 pi r. So we get 24 plus 1/6 times 2 times pi times r, which is 12. That's 24 plus 6 into 12 goes twice. 2 times 2, that's 4. 4 pi. 24 plus 4 pi units. And once again, this is a specific number. If pi is a little over 3, this is a little over 12. 4 times a little over 3 is a little over 12. The whole answer is a little over 36. A little over 36 units. And the pi is just a convenient number to use, but it's a specific number of units here. Okay, let's try one more slightly complicated example using what we know about triangles and mixing in what we have about circles now. Okay, I want you to find the area and the perimeter of this figure. It's a funny sort of figure. What we have is a right triangle, and what would be the hypotenuse of this triangle here. Okay, I want that to be the diameter of a circle, actually of a semicircle, which I'm going to tack on over here. I want the area of this figure and also the perimeter of the figure. Now, the perimeter means the distance around. Okay, so we will not count this dotted line. The dotted line is just to help you see what's going on. That we have the hypotenuse of this triangle also serving as the diameter of this circle, or the semicircle, half a circle. Okay, I want the area of this figure and the distance around the figure, just for the heavy lines, not the dotted line. Okay, let me tell you that this is 12 units from here to here, and that this is 16 units. Okay, and that's all I'm going to tell you. And what we want is the area and the perimeter. Okay, the first thing we're going to do is figure out the hypotenuse of this right triangle. Okay, that is over here. This is the hypotenuse. Okay, let's call the hypotenuse H. Let's figure out a good letter for it. X. Okay, x represents the hypotenuse. Using the Pythagorean theorem, we have here a right triangle. The sum of the squares of the legs, 12 squared plus 16 squared, must be equal to the square of the hypotenuse. 12 squared plus 16 squared must be equal to x squared. Now 12 squared, that's 144. 16 squared, that's 256, x squared. And 144 and 256 come out to be 400. If x squared is 400, that's, by the way, a perfect square. It's 20 squared. It's also minus 20 squared, but x is not minus 20. We can't have the length of this side being minus 20, so we'll only count here the positive square root. X is equal to 20. Although this is a quadratic equation with two roots, 20 and minus 20, we'll ignore the minus 20 since it has no meaning in this problem. And x is 20. That is the hypotenuse of this triangle. By the way, if you're familiar with Pythagorean triples, this is a 3, 4, 5 right triangle times 4. Okay? 12 is, if you have 3 times 4, you get 12. 4 times 4 is 16. If you saw the 12 and 16 and you recognize that this was 3 times 4, this is 4 times 4, then the 20 has to come from the fact that this must be 5 times 4. So you could have skipped this work if you saw that this was a 3, 4, 5 right triangle multiplied by 4. You'd have 12, 16, and 20. Okay, either way, we've gotten now the hypotenuse of the triangle, which means we also have the diameter of the circle or the semicircle. Okay, the radius, therefore, is half of the diameter. The radius is 10. Okay, the radius from here to here is 10. From here to here is 10, to give you the 20. Now, we know enough to finish the problem. The area of the figure is going to be the area of the right triangle plus the area of the semicircle. Semicircle. Okay, the right triangle, or any triangle, the area is 1/2 base times height. And the area of the semicircle, well, the entire circle would have area pi r squared. This has a central angle here that's intercepting this at 180 degrees. It's like a sector of a circle. The angle is 180 degrees, so it's 180 over 360. That's 1/2 the whole circle. Okay, so it's 1/2 pi r squared. It's a particularly easy sector to figure out because it's a half of the entire circle. Okay, the area of the whole circle is pi r squared. For the semicircle, we have 1/2 pi r squared. 1/2 base times height. The base is 12. The height is 16. Plus 1/2 pi r squared, r being 10. The diameter was the same as the hypotenuse, was 20. 10 was the radius. And we get here 2 into 12 goes 6 times 16, that's 96. And then 10 squared, that's 100. Divided by 2, that's 50. 96 plus 50 pi, okay, square units because it's an area problem. That's the area of that figure. Now the perimeter. The perimeter, the distance around, it's going to be 12 plus 16 plus half the circumference of the circle. 12 plus 16 plus this portion of the circumference, and this, since this is half of a circle, we want half the total circumference of the circle. We have 12 plus 16 plus 1/2 the circumference of the circle, 1/2 of 2 pi r. That's 12 plus 16 plus pi r. R is 10. 1/2, the 1/2 and the 2 cancel. We have here 12 plus 16 plus pi r, but r is 10, so we get 28, 12 and 16, plus 10 pi units for the perimeter of this figure. It's 12 plus 16 plus this portion of the circle, which is half the circumference of the circle. The whole circumference of the circle, that would be 2 pi r. We have half of the 2 pi r. Half of 2 pi r is just pi r, pi times 10. 28 plus 10 pi units. And that brings us to the end of the tape.